Hi, good morning, everybody. We'll give just another maybe 30 seconds or so for some folks to log on. This is the SNIA Unlocking Sustainable Data Centers webinar. All right, I think it was about 30 seconds, so we'll go ahead and get started. Thank you all for joining today. The SNIA CMS, the Compute Memory and Storage Community, we're sponsoring a webinar today on unlocking sustainable data centers, optimizing SSD power efficiency and liquid cooling for AI workloads. Today, we have two presenters. I am your host, Cameron Brett. I am a co-chair along with John Michael Hands of the SSD SIG, which is part of CMS, which is part of SNIA. So I'd like to let the speakers introduce themselves. Nicole?
Yeah, hi, my name is Nicole Ross. I work for Samsung as an SSD architect focused on future technology and standards.
Thank you, Nicole. John Michael?
Yeah, John Michael Hands. Yeah, as Cameron said, I'm co-chair of the SNIA SSD SIG. Today, I'm representing Solidheim as an AI technologist. I wear many hats, spending lots of time on AI data centers lately. So it's a fun topic.
Okay, thank you all for joining us today and presenting material on sustainability with SSDs. Just a little bit of housekeeping in the beginning. This quick introduction for the SNIA community. SNIA is a very large organization, industry organization around data management and information technology. Consists of at least 200 corporations, universities, startups, and individuals, with over 2,500 active contributing members from all aspects of these organizations. And basically, the end users range upwards of 50,000 worldwide. So please feel free to explore more what SNIA has to offer, and hopefully you can be interested in joining us. The compute memory and storage community is a community focused obviously on compute memory and storage. What we do is we engage, educate, accelerate, and propel. So we engage the users, educate on these specific topics, promote industry standards that are created by SNIA, and help to propel the technology adoption. And we do this by demonstrating at industry events. You probably attend lots of these events. We host programming workshops and hackathons and things like that. And we also present educational webinars, podcasts, and blogs such as this. Please check out snia.org/group/CMS when you have a chance, and you can learn more about CMS. Drilling down even further, the SSD SIG that John Michael and I are co-chairs of, we place industry information on some specific items, and we want to be basically the place you can go for accurate industry-backed information on things like SSD form factors. There are some new and up-and-coming SSD form factors, as well as the old standard 2.5-inch and M.2. We also reference specifications that you can go find from that page. The NVMe SSD classification page, not all NVMe SSDs are created equal. Some are meant for more specific tasks and environments than others. So the NVMe SSD classification page is a good source for that. And then we have other tools like total cost of ownership calculator that John Michael has created, and he has some other great contributions to the site. So please engage, educate, and get educated. Check out the SSD SIG page, and either reach out to one of us on LinkedIn, or if you want to learn more, you can go to askcms@snia.org. One last housekeeping slide, the legal notice. I'll leave this up here for just a few seconds, but this is a standard legal notice. The material is copyrighted, et cetera, no warranties, et cetera. And without further ado, I'd like to turn it over to John Michael Hands, and he can kind of tell you what he's going to talk about, and then we'll get things kicked off.
Awesome, excited. Yeah, we were going to, I was doing these slides over the weekend. It's kind of interesting. I thought a lot of the impact for how we talk about SSD power, you really have to understand some of the larger trends and what's going on in the data center. And hey, since we have sustainability, in the title of the talk, I thought I'd start with we did a SNIA OCP partner update, I think in the fall, like November or something last year. I was chairing one of the OCP sustainability projects in circularity, and we wrote a white paper, I think like 2 years ago in OCP around what sustainability means to the ICT industry. And I still find that most folks get this wrong, where what we were describing is the three categories that we came up with were transparency reporting metrics, which is all about actually reporting emissions, scope 1, scope 2, and scope 3. And for suppliers, it really means talking about life cycle assessments. We spent a lot of time talking about circularity. I'm the president of Circular Drive Initiative. It's a nonprofit all about circularity and sustainability and storage, about media sanitization and reuse of drives instead of shredding them. But today we're going to focus on efficiency. So really, there's and one of the key focuses in the white paper was kind of talking about efficiency beyond PUE, of understanding the IT equipment in the rack. But just to recap, a lot of people say sustainability when they actually mean efficiency, and they're two separate OCP tenets and very different things. Efficiency is one part of sustainability. And this, I thought I'd just throw this in there because, again, I've seen a lot of people kind of get this wrong, and there was a lot of press around this, kind of white paper that Seagate released, a couple, like last month or something like that, which I thought it was a fantastic paper, by the way. And they have this table in here that describes the embodied carbon of per different storage media. And so one thing is that efficiency is all about the use phase, like how much energy does a device use while it's in use. And in the use phase typically for an SSD, say, for 4 to 5 years, now kind of extending, people are thinking about longer deployments, like 7 years. And so it's pretty easy to calculate the carbon impact. People say that, but that's from the use phase. And in a full life cycle assessment, you'd show, okay, how much energy does this thing use over the life cycle of the device? And then you can calculate, the carbon impact. Embodied carbon is something completely different. That is how much carbon it takes to manufacture the device. And so everything leading up to the manufacturing. So in the SSD case, most of the embodied carbon comes from the NAND flash itself, from the manufacturing. So now the study that they cited in this report, it was an older study that was looking at different life cycle assessments of SSDs. I think right now it's probably around 50 or 60 grams per gigabyte or kilogram per terabyte. But yeah, again, just to understand, like when you talk about sustainability versus efficiency, that they are two different things. And hopefully we get a lot more life cycle assessments done in the SSD world, because we haven't seen as many vendors put out longer life cycle assessments. But so now shifting gears to energy in data centers, right? This is obviously a huge problem, right? With 60 gigawatts of global IT energy, and all this blue. This is the semi-analysis growth coming from AI data centers. Obviously, all the new builds are coming online with AI data centers. This was just from 2005 to 2024. You've seen just tremendous growth in data center type between enterprise, co-location, hyperscale, and electricity consumption. Obviously, the servers can contribute the most, but other IT equipment and then the cooling, this is kind of the overhead and the PUE of the data center. So making the drives more efficient, from a cooling perspective, is going to save quite a bit of global electricity consumption, and we'll kind of talk about how SSDs play into that. But there was a study done by Microsoft and Carnegie Mellon on basically call for action on sustainability in storage and lifecycle assessments, and call to action for looking at understanding the emissions of storage. And in that, they said storage racks at Azure could make up for instance, 33% of operational emissions. So it's not just a small part of these hyperscale data centers. It is in fact a very, very large part. You can imagine, right? There's hundreds of exabytes now of SSDs sold every year. Zettabytes of hard drives. Storage make up a large chunk of data center power consumption in that global data center consumption. So I did do on my docs.farm GPU site, I have a little AI data center teaser where you can, if you want to go learn about AI data centers, there's a full nice page that I've created there, and this table is from there. But this is when I say AI data centers, this is what I mean when I say AI data centers, right? It means that it's a data center focused around GPUs and accelerators. It's the kind of workloads that are running in an AI data center are model training, inference, fine tuning. They're AI workloads. The memory architecture. Most of these AI are dominated by HBM and on accelerators. As far as like the CapEx where the memory is coming from, networking. These are where it wasn't very common to see like super high speed, peer-to-peer networks of 800 gig fabrics in data centers. Now it is very common for AI data centers because these GPUs need to talk to each other at full bandwidth for training runs. The biggest impacts that we're seeing as far as the data center infrastructure side is the rack power density and the cooling capability. So we'll talk about rack power density, but in an AI data center, it would be very typical to see 40 to 120 kilowatt racks is what's being typically deployed right now, and we're going to discuss like that trend is continuing to increase up. So liquid cooling, and there's a bunch of the topic we're going to spend some time on today is helps the efficiency side as far as lowering the power from obviously deleting the fans and having more efficient cooling infrastructure, and that can be done with direct to chip or immersion. Some people say liquid cooling kind of just mean direct to chip. But we'll talk about how it's really impacting the density of racks. And the other stuff you can see just kind of like the economics and key software stack and whatnot. If you want to learn more about this, I have a whole website that I've created on AI data centers that kind of fun to go dig through. But now OCP, this was again something they had they had a workshop about a month ago on this OCP AI ML physical infrastructure workshop, and they said, okay, if you want to be a AI data center, what OCP came up with was actually very similar to what I came up with: high power racks, liquid cooling, optimized power networking, enhanced data center physical infrastructure, and then sustainability metrics and reporting. In the workshop, Microsoft and Meta announced this. I think Mount Diablo, I think, is the code name, but this path to 600 kilowatts to a megawatt rack. Now, a megawatt in a single rack. This is what typical older regional telco data centers were. An entire megawatt was an entire data center, for the entire IT equipment, not just that. Now it's basically one rack, which is, just absolutely insane to think about. And the reason for this is, in my opinion, this is just my take, is that this CapEx density, where if you're, Microsoft is spending $80 billion on data centers this year, for CapEx between IT equipment and the data centers, or if you're, Meta's, I think I announced that they were increasing their spend to $72 billion this year. Well, if you do that 40 kilowatt racks at a time, it's going to be a lot of racks. So now this is a picture of the Meta Primeville data center, which I think I toured a long time ago back at Intel. But why am I showing a picture of this data center, right? Well, in 2023, they said that they had a PUE of 1.08 and a water usage effectiveness of 0.18, which is like absolutely world class on both sides. But the key in this data center is that there were data centers in this 2011 to 2015 timeframe that had below a 1.1 PUE, and at the time the average PUE, the best in class was like 1.5 or 1.6. And power usage effectiveness, basically the overhead of how much power gets used for cooling and everything else in the facility that's not going to the IT equipment. And this is really important to note of the why liquid cooling. So again, that hyperscalers were able to get to a very low PUE with air cooled only, with evaporative chillers and different cooling technologies. And in this data center case, it's about the actual geographic location and ambient temperature and all the stuff that they played there. But really, this move to, and it took me a while to understand this move to density and to high megawatt racks forces the need for liquid cooling, this direct to chip. Immersion is also extremely dense, and you get you basically get a 2-for-1. So when you get you solve this rack density problem, but you also solve the efficiency problem and the PUE, because now you've deleted the fans, you've made it more efficient. But now these aren't free. You have to basically, if you're in a data center, get a CDU. You have to have water coming into the facility. So there's quite a bit of understanding that has to go in before you go to liquid cooling. Now, the exciting thing that Solheim announced at GTC was this partnership with NVIDIA on the GB300 reference design for enabling liquid cooling on the SSD. So this is one of the last components in their current GB200 NVL72 rack for NVIDIA. There's there's liquid cooling obviously for the GPUs and the NVLink switches, but not for SSD. They still have fans on the servers for those. So this move to liquid cooling is very cool for lots of reasons. One, obviously, you can delete the rest of the fans on the rack level system. So now you can just do liquid cooling for the entire solution. But this enables now potentially options for higher power SSDs, where before you were very limited by air cooled just in the actual physical dimensions and the form factor of the ESFF specs. So there will be some exciting changes, I think, to E1.S. Actually, the changes, from my understanding, of talking to the technical guys, to enable this solution for liquid cooling on E1.S is actually fairly trivial. It's like 2 minor things in the spec that they're going to change. So yeah, excited to see this kind of come into production this year. Okay, shifting gears again to efficiency for SSDs. We talked a lot about efficiency and how do you measure efficiency on SSDs? So one thing, and this is just a sample from Solheim had versus one drive versus another, just kind of how they're showing the comparison of like performance per watt or IOPS per watt in some different workloads. But the right way to approach this is, for a compute SSD, the metric of goodness for efficiency is IOPS per watt and bandwidth per watt. It's like how much performance are you able to deliver at a certain power envelope. And you'll see that efficiency comes from the SSD controller as well as the NAND. So you can't, if you don't make the NAND more efficient every generation as far as performance per watt, then it will be obviously very, very challenging to improve the overall efficiency, even if you just improve the controller. Now, for storage SSDs, really the efficiency that people will talk about are terabytes per watt. So making the SSDs larger capacity, larger rack density, and TCO. And I'll give you kind of an example. Of course, we have the SNIA TCO model that I'll show you that we are updating, in the process of updating the 2.0 right now. But this is really how customers think about the efficiency for storage type SSDs. How much storage can you fit in a rack, and effective capacity and whatnot. Now, this is very different from consumer SSDs, where efficiency is measured in battery life. People really care about going to idle power. These lower NVMe power states, autonomous power state transitions, PCIe L 1.2, things to basically get to zero idle power with a very fast resume. And the key in this one is that consumer SSDs have already demonstrated that we can get to near zero idle power with almost instant resume. So right now, I think some of the best consumer SSDs are around 5 milliseconds resume from like zero idle power, which turns out is the random read latency of a hard drive. So that's actually extremely interesting for storage SSDs when we move from we move SSDs into colder tiers where they're going to be idle a lot more often. You need to start worrying about idle power, where right now, it's maybe 4 to 5 watts for a typical data center SSD for idle power. Now, the way you think about, there's a big transition going on right now from PCIe Gen 5 to Gen 6 in the SSD controller planning world. And one very interesting thing to think about is controller power versus NAND power. And you saw, because in the first generation of Gen 5 SSDs, that a lot of vendors had to kind of frantically figure out how to move now from 12 nanometer to maybe 5 or 6 nanometer, basically to get this controller power down. Because if you think about I've shown here, this is kind of capping the SSD at 16 watts. This is capping the SSD at 18 watts. This is capping the SSD at 20 watts. This is capping the SSD at, say, 25 watts. And if the controller power stays the same, this is like 3, 5, 7, and 9 watts for the controller power. You can see the NAND power. It's obviously, as you get to these ends where there's more controller power, you have less power for the NAND, which means, in the same constraint, your performance is going to be a lot less. And so it's hard to think about, but when you're at these lower levels where you want to lower the TDP of the SSD, and hyperscalers back to that Meta example with the prime build data center, one of the key ways that they got this really low PUE was from very intelligent fan speed, and using the right form factors for SSDs like E1.S 25 millimeter to have optimal cooling. So in these power constrained environments, it hurts more when you lower the power if your controller power is higher. So it's very, very important to understand this ratio where potentially, again, when we get to PCIe Gen 6 and if the form factors stay the same and the power is capped at the same spot, but you need to deliver twice the performance, and your controllers, maybe you can make 30 or 40% more efficient, or even 30% more efficient, or something like that, then that becomes a bottleneck. So all of a sudden now we have this opportunity that, hey, if we were able to go to even 30 watts or 35 watts, maybe we could double the SSD performance. Well, now all of a sudden with liquid cooling, that's a total reasonable thing to do. So one of the new things that's coming in the OCP and NVMe SSD 2.6 spec, they call it the DSSD data center SSD spec, is this new NVMe DSSD power states. And again, there's already the NVMe SSD power state descriptors in Identify Controller that tells you, what power states the drive supports. And typically, you can basically cap the drive's power through just sending a NVMe set features command. Now, this is a pretty easy way to do it, but you have to know, okay, I have to read the Identify Controller information, see what power states are available, and then set it to power state 0 or power state 2 or whatever, based on my understanding. Now, the DSSD is opposite, right? So if you actually just send it whatever power you want, and it will automatically pick the power state that's closest to that. So instead of having to query the drive and then find out what power states it supports and then send the correct power state, you can just say, I want this drive to be a 14-watt drive, or I want this drive to be a 18-watt drive. So this is a very cool feature coming in OCP 2.6. And Nicole will talk a lot more about some of the cool stuff that NVMe has done on the space. Now, of course, how we can't talk about the exciting opportunities about efficiency without talking about kind of hyperscale TCO. And so now, exciting teaser in the new version of the SNIA TCO model, we have kind of a hyperscale representation. Thankfully, in the OCP Grand Canyon spec, they had kind of the configurations for a warm storage rack and cold storage rack, and the ratio of compute to JBODs and all that stuff in there. And I'm just kind of playing with this announcement that we talked about E2, this new form factor that will enable the super high capacity drives. Now, I was obviously a big fan of E1.L, but a lot of people don't necessarily like 1U chassis for storage, and they'd like to go to these 2U chassis. So I think this is just a great upgrade to the family of EDSFF, to basically have these super options for super high capacity drives that fit native in a 2U chassis. But the example they gave was, say, for instance, 40 devices in a 2U chassis scaling up to 1 petabyte. So 40 petabytes per 2U, that seems pretty insane. So large capacity trends, 122 terabyte SSDs are shipping. The C2 form factor has been designed, and QLC adoption is growing. Meta has kind of showcased this at back here. Meta's showcased this at the at scale conference. They were discussing this this adoption and their plan for QLC, and then obviously there's a bunch of new NVMe features to minimize write amp, like ZNS and FTP. Most of these vendors are using kind of lower amount of DRAM or larger IU sizes to reduce costs. And these large capacity SSDs, can improve terabytes per watt. But that system level stuff that I mentioned, this 2U, 40 petabyte kind of path, this system plus SSD improves your petabyte per rack, which is the metric of goodness there. And right now SSD is obviously 1,000 times faster than hard drives, but your bandwidth per terabyte, if you make the drive all of a sudden 512 terabytes and you only had 25 watts, now all of a sudden we have to kind of talk about what the right performance level is for the SSDs. So with that, this is kind of like a little teaser for our new model that's coming, but this will be one of the examples in the cloud source. I don't remember all this. You guys will have access to this. It'll be all open source, but about kind of what I put assumptions in here. But I'm just saying, what if we have this, for instance, 512 terabyte SSD at 3 cents per gigabyte, this made up thing in 2027 or something like that. Maybe it's maybe we don't get quite that far, but with the cost. But hey, SSDs are faster and they have more IOPS, so you can have compression, data reduction, that kind of stuff can be improved on SSDs with erasure coding. Obviously you'd have a reduced OpEx percentage of TCO. This is just kind of in a hyperscale TCO model. But we talked about terabytes per watt, but I think a very fun metric I came up with during this was exabyte raw per megawatts. Like how many exabytes can you fit per megawatt in this? Just between say hard drives are at 36 terabytes and 512 terabyte. I don't know what they're going to be at in a couple of years. Maybe 36 terabytes or 50 terabytes. But this would be a 15x difference in rack density for the same power. So just a metric of goodness and something to think about for these power constrained data centers. So with that, I'm going to turn it over to Nicole. Thanks, guys.
Hey, thanks, John Michael. Real quick, before Nicole jumps on, I just want to remind everybody, if you do have questions, please type them in the question box, and we will get to them as soon as we can at the end of the webinar. And whatever we are not able to answer today, we will have a follow-up blog that addresses all the questions. And with that, I'll turn it over to Nicole.
Thanks, Cameron. Thank you all for attending. My name again is Nicole Ross. I work for Samsung as an SSD architect. Today I'm going to talk to you guys about something I've always found interesting, which is power, and then pairing that up with power efficiency piggybacked on NVMe. I'll keep it short and sweet. All right, so why does power efficiency matter? John Michaels kind of went over this already. AI is starting to require a lot more sustained throughput, which means a lot more power. These are in GPU-dense servers, which require a lot of cooling resources. That leaves storage with the leftovers of those thermal resources. Data centers are going to start spending a lot more of their budget on power, and there are up-and-coming sustainability goals and regulations that we're all going to have to try to meet or exceed. All right, so again, I think you guys heard a little bit about what NVMe power states are. There's power states in NVMe and OCP. What were these typically used for? Power budgeting. If the rack is only capable of a certain amount of power, then it needs to distribute that power amongst a lot of different hardware resources. Also for idle state efficiency, if the platform is not being used, then we need to put those devices to sleep. There are 32 power states within NVMe that are defined by an SSD. Those power state descriptors that was already discussed describe what the max power is, what are those exit and entrance latencies associated with that power state. Today, I'm going to talk about the host setting the drive into these power states via set features, but the drive can enter autonomously into those states. What I'm suggesting to add is some workload awareness to those power states. All right. So what's coming in the pipeline within NVMe? So the problem with what exists today is there's no scalable or standardized way to be able to report power. It requires external hardware or vendor unique tools, which is expensive and not scalable. TP4199 is self-reported drive power. This is going to add that capability, and it's going to add more functionality. We're going to get two things within the smart log page. That's going to be 1 second power averages, and then the lifetime energy consumed, which can equate to carbon costs. There's very importantly, there's this power threshold exceedance interrupt via an AEN. This is going to allow for the host to make real-time decisions and reactions to unexpected power draw. There's a possible log page as well. That log page will have average power over time, maximum power, and a histogram. All of this being standardized and scalable. For more information on this, there's an OCP tech talk on YouTube. You can go there and it digs a little bit deeper. Okay, so a lot of the innovation, there needs to be some innovation onto the host and some onto the SSD to make this work. The SSD is going to need onboard power rails to be able to detect its own power draw. We're going to have to implement TP4199 to be able to report to communicate that power. And then we're going to have to really do some innovation here with creating these power states and determining what they look like from hardware and a firmware perspective. These are going to be needing to be described clearer power caps, latencies, and perhaps performance hints to allow the host to make accurate decisions and accurate mapping. These states should be cleanly mapped to AI phases or specific customer workloads, and that'll allow the host to dial in exactly what the drive needs and nothing more. All right, let me talk about a happy path example of what this could look like. So the host knows already what power states the drive supports. It's able to take those states and map it to a specific workload or an AI phase. I'm going to talk about possible our proposed AI mapping. All right, so the host is about to do some training. It will issue a set features, placing the drive into PS0, which is in NVMe, the highest power state, so that the drive it knows that it's going to start doing large sequential writes, which requires the most power and then the most cooling resources. Later, the host could switch to inference by issuing a set features, assigning a new power state. We know inference is mostly reads. There's going to be various I/O sizes of reads, sequential or random, depending. That's all going to change up the power resources. And the main thing to take away from inference is it is going to require really low latency and high throughput processing. So we really need to design for efficiency here on this one. And then when the rack isn't being used, we need to be able to place hardware into idle states and various different idle states, not just one, because we need to make sure that the host is able to wake us up and we can perform I/O within a certain amount of time. So while all of these workloads are happening, the host is going to pull for our power telemetry. It's going to validate that our power telemetry is correct, that we're within a specific threshold that it expects. So what happens when we're not within a specific threshold? This is the non-happy path example. This is where the host needs to be reactive to be power optimized. So yeah, even the best planned power state assignments will face runtime surprises. The host needs to use this power telemetry to make real-time decisions. And so if there is a power breach, the host is going to need to do some power balancing and move workloads off of an SSD or pull in more cooling resources, whatever that takes to make the rack balance out. There could also be potential SSD anomalies. That has been a case in the past where we see possible extra NAND background activity or other various issues that could be pulled out by being able to read power telemetry. So that'll enable that on the fly. There's also the possibility that there could be a host to drive workload mismatch. We'll be able to determine this early. The host can make different decisions based on what the power is, if it's actually delivering the correct workload to the drive that it expects. And then it'll be able to either reassign or understand possibly an issue on the host software side. All of these pulled together are in the goal to increase power efficiency, which will reduce the power bill and lower the TCO costs, and then support our sustainability goals. Wrapping all of my material up, we know that AI power is high in demand. There's a need to be able to become more and more power efficient. This is causing power to be a first-class design metric. We didn't have a way to be able to pull power telemetry in a standardized, scalable way. TP4199 is adding that. I'm starting the conversation of using dynamic power states to be able to communicate workload awareness and power efficiency to the host to make real-time accurate decisions. All of this to be able to increase power efficiency and cut costs, which will lower TCO. And then we all have greener data centers without sacrificing IOPS. That's all I have for today. Cameron?
Okay, thank you, Nicole. Appreciate the information here. Let me go ahead and go to the next slide for questions. We do have a couple of questions, but before we jump into the questions, Nicole, where would be the best place to get more information on the TP you were discussing and other NVMe information?
Right, so you can join the NVMe technical working group. NVMe will post all ratified material and NVMe specifications on their website. And there is a deeper dive into TP4199 on YouTube. I'll attach the link onto my slides and publish them. But if you search for 2025 OCP Storage Tech Talks, it'll show up.
Okay. Thank you. And John Michael, you have a lot of information there. Is there, I guess, a couple of sources that you can provide so that people can dig a little bit deeper?
Oh, absolutely. Yeah, I mentioned, let's see if I can add them, or maybe, I guess, usually we have a blog post after we release this on the SNIA website where we kind of like post all the links. I'll just kind of post some new links to some of the new TCO models we're working on, some of the documentation I mentioned. We have a bunch of exciting training and learning about AI data center stuff, and yeah, it's just all kinds of good stuff we can post.
All right, so we'll just provide a more comprehensive list of locations to get more details from your information. Okay, do have a couple of questions here. Let's see, this one is. I'm not sure who this is geared towards. It came in during Nicole. So what kind of switching times between power states are being considered? I think you're on mute.
I am on mute. Okay, so that is a tricky question because it is dependent on what specific power state it is and what needs to be done onto the SSD to get it in and out of that power state. If we're talking about idle states, that's typically where hardware components are going to sleep, and that takes time to boot up and spin up. That's going to be a little bit more into the millisecond range. Other power states can be within the microsecond range.
Okay. Let's see, another question here. It says, what type of usage is assumed for TP4199 in system rack data at the data center level? I was trying to get a little bit more information on what type, what do they mean by usage, but is that something you might be able to discuss?
Yeah, okay, so I did talk through a couple of usage models. There's actually a lot of usage models. If you sit down and think of how we could take power, if you worked in validation or you're familiar with SSD power, you can backward reverse engineer what's being done. You can take a lot of that information and be able to on the fly get bug information. You can optimize your host software better. You can compare SSD vendors saying, okay, well, Samsung is this, Micron is this, why is there a discrepancy? We want you to be as good as X. So there's that validation use case amongst different vendors. There's also being able to reach sustainability goals within the rack. I know that all of compute customers are really stepping it up with their sustainability initiatives. And in order to do that, they need to look at each hardware component.
Okay. Thank you, Nicole. One additional question came in saying the information that presented today is focused around data centers, but AI is moving to the edge. So is there a place that people can go for more information on the same type of content, but for the edge? I guess that's open to both of you.
Boy, yeah, I've let's see where there's the folks that I'm talking to on the edge are really interested in immersion, which is interesting, because I mentioned for the hyperscalers, this density per rack is all focused on liquid, and the immersion stuff actually turns out to be really interesting on the edge, where there could be heat reuse or whatnot. But I think edge used to kind of mean like really edge smaller pops with like 1 or 2 type servers. Now I think people are saying edge more of like on-prem, regional data centers or telco data centers. A couple megawatt might still be an edge, on-prem thing. So yeah, no, certainly very, very interesting as far as the types of power and stuff. But for the SSD, I think obviously that liquid cool one is an extreme example where people aren't building 600 kilowatt racks on the edge. They're building like 20 or 30 kilowatt racks. So that's kind of the major difference, right? I think is where I see edge is still more enterprise, traditional data center. You have extreme power limitations on the rack, where actually maybe maybe some of these NVMe power states actually become even more critical.
Okay, thanks, John Michael. Anything to add, Nicole?
No, nothing.
Okay. I think we'll have time for one more question here. What are your thoughts on balancing serviceability with cooling performance for direct-to-chip? For example, using TIM.
So I think at least the interesting thing that in the solution I showed you, and I guess, sorry, there's probably a lot more slides we could show you on that solution for the E1.S liquid cooled cold plate solution, is that actually they designed a way to make the E1.S hot pluggable with the cold plates. So it's still, the SSD is still serviceable in the liquid cooling system, which is pretty unique. And I guess, yeah, SSDs have always been this thing. We want them serviceable to be able to replace it with any failed drive or whatnot. But yeah, the immersion thing too. And I always thought that there'd be no serviceability in immersion, but turns out you can just pull the thing out of the tank, let the fluid drain, and then swap stuff. So yeah, it's we'll just say in production stuff has been pretty surprising to me. But yeah, liquid cooling is certainly it makes this higher power density makes everything a million times more complicated. Like it's a lot harder. Like this is a lot harder than air cooled stuff.
Okay, thanks, John Michael. Okay, I think let's move to wrap this up. So thank you for attending, everybody. Just a couple of things, last bit of housekeeping here. Please rate the webinar and provide some feedback, whether you like it or have some suggestions for improvements. As noted before, we will provide a blog with answers to these questions, and if any additional come in, then we can answer them. Come check out SNIA. Will be in presence at FMS, the SDC conference in Santa Clara, and supercomputing in November. And then we have the online resources, the SNIA Educational Library, and the YouTube channel. So please join SNIA and the SSD SIG. There's a number of links down there where you can get more information. And I think with that,
yeah, there's one last question on their standardization activities for SSD form factors and liquid cooling. That's a fantastic question, by the way. That was one I had when we were kind of doing these slides about. There is, I guess, there has been some discussion started in SNIA SFF about this. So yeah, I'd love to. I guess maybe that's a great action to kind of bring that to light as in the blog, as far as what work has been done so far and what is planned for the rest of the EDSFF form factors around liquid cooling. But yeah, it definitely opens up. I know even that E2 form factor, they talked about support for up to 80 watts in the form factor. But yeah, I mean, it seems like liquid cooling would be very advantageous for not just the hyper, not just the compute side.
Understood. Okay, thank you, Nicole. Thank you, John Michael. And at this point, we will go ahead and end the webinar. Thanks for attending, everybody.
Thanks all. Bye-bye.
Thank you.